Hey everybody. This is the supplement on directional derivatives and the gradient vector, section 14.6. This is the second supplement for week 4. So we'll be covering section 14.7 on maxes and mins in tomorrow's class on Wednesday, and then 14.8 on Lagrange multipliers will be the third supplement for the week coming out on Thursday. And that will wrap up our week and chapter 14, and then next week we'll start into chapter 15. Okay, so starting into directional derivatives, recall the definitions for the partial derivatives, partial f with respect to x and partial f with respect to y. They were defined this way. Note that, for instance, the partial with respect to f, or with respect to x of f, we vary the x coordinate but leave the y alone, and vice versa with the y partial. These partials represent something like instantaneous rates of change in height of the surface, z equals f of xy. When we're looking at intersections of that surface with planes parallel to the coordinate planes, either the xz plane or the yz plane, through that point, x naught, y naught. So let's try to draw a couple of pictures here. So here we have x, y, and z. We have some surface. Like this. And for instance, if we want to look at the partial f with respect to x, we're thinking of fixing our y coordinate, considering a point, say x naught, y naught, on below the surface, and x naught, y naught, z naught on the surface. So x naught, y naught is this point down here, and on the surface is the point x naught, y naught, z naught. And then we're thinking of a plane. I'll try to draw this in a somewhat sensible manner. We're thinking of a plane that's parallel to the xz plane that goes through this point x naught, y naught on the xy plane, and through the point x naught, y naught, z naught on the surface, and it intersects the surface in a curve. So if I imagined pulling this plane out over here, I would have a curve something like this, where this corner is coming over to here and this corner to there. I would have a curve that looks something like that, and I would be thinking of, roughly speaking, x as being like the independent variable, the horizontal axis, and z as the dependent, roughly speaking, from this context. And again, I could imagine at this point of interest, I would have a tangent line here that's represented by a tangent line over here. I could draw a similar picture for the partial of, and this is the line associated with the partial of f with respect to x, because x is the variable that's varying while y is held constant at y naught. And I could draw a similar picture for partial with respect to y. The plane would just be going left to right instead of kind of front to back. But I might ask myself, okay, what if I had this surface? Let me try to draw it again. What if I have this surface, like I have over here? And remember, over here in my input space, I was interested in what happened as I kind of varied along this straight line parallel to the x-axis. I held y constant at y naught and moved x from x naught plus a little bit to x naught minus a little bit. Or I did just the opposite for the partial with respect to y. Well, what if I was interested instead in, say, a line in the xy plane that wasn't parallel to one of the X or Y axes. So something like this line, maybe that's like a 45-degree line between X and Y. Well, again, I could just as well imagine that this line is the intersection of a plane with the XY plane, and that this blue plane intersects the surface along some curve. And just as before, I could imagine that at some point on that curve, I could have a tangent line that is in this plane, and I could be interested in the slope of that tangent line, the instantaneous rate of increase of my output z as I vary along this this input line that is not necessarily parallel to the x or the y axes. And this is the idea of a directional derivative. So investigating a similar idea to partial derivatives, but for input lines, so to speak, where that are not necessarily parallel to the x or y axes. Okay, so let's consider a unit vector u equals ab. And this will serve as the direction vector for a line in the xy plane, this kind of line of interest here that's in the domain of f. And we're interested in the rate of change of the output at a point on the surface, this point up here, z naught equals f of x naught y naught. Oh, that should be a f of x naught y naught. So this is our x naught y naught point. And this height is z naught. Then the line through this point, x naught y naught, in the direction of u, ab, we could write as r of h equals x naught plus ha, comma y naught plus hb. That is just the representation of this green line up here that's lying in the xy plane. That's the direction of interest. Again, the partial f with respect to x, that line only moved along the x component, not along the y component. So b was just 0 in that case. And in the other case, the partial with respect to y, a would be 0. But here, we're looking more generally where we can have both an x and a y component of that movement, of that direction vector. And we can say the curve representing the intersection of the surface, z equals f of xy, this black surface up here, with this plane that's defined by just taking this green line and kind of stretching it up and down along the z direction. We can say that that curve is f of x naught plus ha, comma y naught plus hb. So that is this curve here. Okay, so let's formalize this into a definition. The directional derivative of f at the point x naught y naught in the direction of a unit vector u equals ab is, we use this notation, capital D subscript u vector. So that's a bold u in the subscript. Or if I write it by hand, I'll write it as a u with a vector bar over it. So du f of x naught y naught is the notation we'll use for the directional derivative in the direction u at the point x naught y naught. We take it to be the limit of f of x naught plus ha, comma y naught plus hb. So this output here, minus f of x naught y naught over h. Or we could write this in vector notation as something like f of x naught plus tu, where here x naught we're taking to be a vector, So here, x naught vector is x naught y naught, is x naught scalar in the first component and y naught scalar in the second component. We'll see why it's really nice to write this in this vector form in a little bit. It makes generalizing this idea so much easier. So we could take f of x naught plus tu, the derivative of that with respect to t, and then evaluate that at t equals 0. And that's saying the same thing that we have over here. And this is, of course, provided the limit exists. Okay, a couple notes on this. First, it's often convenient to write a general unit vector, u equals ab, as u equals cos theta comma sine theta. Note that cos theta sine theta is obviously the representation of the unit circle. So any unit vector, if it has length 1 and points in whatever direction, can be written in this form. It's going to have, if the initial point is at the origin, it's going to have a terminal point on the unit circle. So any unit vector can be written in the form u equals cos theta sine theta for some choice of theta. And any vector written in this form is a unit vector by the Pythagorean identity. Its length is going to be root cos squared plus sine squared. Its length is going to be 1. So that's going to be helpful coming up here in a couple of cases. Second note, if we take our direction for our directional derivative to be just I hat or 1, 0, or just going along the x-axis, we note that this can be written as cos 0 comma sine 0 as well. Then our directional derivative, well, our direction is 1 comma 0. So a is 1, b is 0 up here in the definition. So we just get limit h goes to 0, f of x naught plus h comma y naught minus f of x naught y naught over h. But that's just the x partial at x naught y naught. And similarly for the direction in the y direction, j hat, we just get the y partial there. So the directional derivative is a generalization of the idea of partial derivatives. Again, we saw that kind of geometrically looking at the pictures, that was the motivation, but we see that very clearly in the algebra now as well. Or we could put it another way. We could say the partial derivatives that we've encountered previously, they were just a special case of this more general idea, albeit a very important special case. So just because it's a special case doesn't mean, I don't mean to trivialize it. Partial derivatives are extremely important, but they're a special case of this idea of directional derivative. And in fact, respecting this idea that a directional derivative is really kind of a partial derivative, a lot of books, or some books, use the notation, instead of capital D sub u, they use the little partial d sub u, I can't think of its name, it's just escaped me the name of that symbol, but the partial symbol. So some books actually use that, and that's obviously a nod to the fact that it's essentially a partial derivative. It's getting information about how the changes in the inputs relate to the outputs, but only in a certain direction, only along one particular direction. Okay, so let's take a look at example 1 here. We're going to compute the directional derivative of f at the point -2, 1 for this function f, x squared plus 5y squared, in the direction u equals 1 over root 2, 1 over root 2, which is a unit vector. And we're going to use the definition of the derivative to do this, the directional derivative. So we are going to use this definition, which I will copy down here. Okay, so this derivative by definition is limit h goes to 0 of, well, let's just write out what everything is first. So that's going to be f of I want to keep my points and my direction separate. So I want to just note that this is x naught, y naught, and this is a and b. I'll note that just so I don't get them backwards or something. -2 plus 1/√2h, oops, for my first argument, and for my second argument, 1 plus 1/√2h. So that's f of x naught plus ha, comma y naught plus hb, and then minus f of x naught, y naught is -2, comma 1. All over h. Okay, so now what do I do? Well, now I have to evaluate f a couple of times. So f says square the first component. So I get -2 plus 1/√2h squared, and then add 5 times the square of the second. And then subtract off f at -2, comma 1. So subtract off -2 squared, and subtract off 5y squared. That's all divided by h. And what do we get in the numerator here? We get -2 squared is 4, plus 2 times the first times the second. So that's going to be minus 2 times 2 is 4 over √2h. And then plus the second squared is going to be plus 1/2 h squared. That takes care of the first term on the top. The second term on the top is going to give me a 1 squared is 1 times 5 is 5. The cross terms give me a 2 times 1 times 1/√2. So it's going to be a 2/√2, or I suppose just the √2 multiplied by 5. And then 1 power of h there. And then my last term is going to give me what? It's going to give me 1/2 h squared times 5. So plus 5/2 h squared. And then I have -4 minus 5 all over h. Now I see I get some stuff that cancels. The 4 and the -4 go away. The 5 and the -5 go away. And I can divide out an h now. So I get, well, -4/√2 is just -2/√2, I suppose. Once the h divides out, plus h over 2 plus 5/√2h. Plus 5/√2, the h divided out, plus 5/2 h. And now it's easy to take the limit as h goes to 0. These bits drop off, and I get 3 square root of 2 as my answer. Okay, so that was a decent bit of work, and that was even for a, not too, a function that wasn't too bad, just the quadratic. You could imagine that a sine or an exponential or something is going to be quite messy. We have this super nice theorem that we're going to make heavy use of, though. The theorem says that if f is a differentiable function of x and y, then f has a directional derivative in the direction of any unit vector ab. And furthermore, that directional derivative can be calculated as the partial with respect to x at x naught, y naught times a times the first component of u, plus the partial with respect to y at x naught, y naught times b, the second component of u. Or if we wrote u as cos theta sine theta, it would look like this. Note that this structure, fx times a plus fy times b, kind of feels like a dot product, right? I have a and b are the components of u, and if I make another vector that has components partial f with respect to x of x naught y naught is the first component, and partial with respect to y is the second component, then this just turns out to be the dot product of that vector with the derivatives in it with the vector that's the direction vector. Okay, let's prove that this is true. And for this, we're going to use kind of the second form of our definition, which I'll just copy down here. So we're going to consider this, this version of the definition. Okay, so let's calculate out what this actually is. Well, we can say a little more explicitly, this is the scalar x naught plus t times a in the first component, and the scalar y naught plus t times b in the second component. That's what x naught plus tu is as a vector. We want to take the derivative of this function with respect to t, and then evaluate that at t equals 0. Now, nicely enough, we've just covered the chain rule. So this is what? This is the partial of f with respect to x at x naught plus ta, y naught plus tb. This is a bit to write out, but I think it's good to be careful going through all this because there's just a lot of moving parts. Partial f with respect to x times dx dt. So dx dt is that the derivative of that first component with respect to t. The only variable in here is t. There's not some other independent variable, so we're using normal derivatives here. And then plus partial f with respect to y of, just like before, x naught plus ta, y naught plus tb, and then similarly dy dt, using a normal derivative for the same reason as I mentioned before, and all of that has to be taken when t equals 0. But dx dt is just a, and dy dt is just the constant b. And then if I plug in t equals 0, I can see all these bits in the inputs 0 out. We're assuming that that the partials are continuous and so on, so that we can move the t equals 0 inside. So what does this give me? This gives me the partial of f with respect to x at x naught comma y naught times a plus the partial f with respect to y at x naught comma y naught times b. And that's exactly what we wanted to show up here. The other bits, this piece with cos theta and sine theta, and this piece with the dot product, are just other ways of writing that same thing. So that completes our proof of that theorem. As an aside, your book does it a slightly different way, so there's a couple of different ways to approach this proof. Okay, so let's revisit example 1, where we computed the directional derivative with the definition. Let's revisit it and use the theorem. So again, the theorem just says that I multiply my partial derivatives by the components in the direction vector. So I need my partial derivatives. I need df dx for x squared plus 5y squared. Well, that's just 2x. And fy is 10y. And importantly, I need the values of these partials at the point x naught, y naught. So these should end up being numbers, not things with x's and y's floating around in them. So when x is -2, my x partial is -4. And when y is 1, my y partial is just 10. And I also note that a equals 1 over root 2, and b is 1 over root 2. So then my directional derivative should be partial f with respect to x times a plus partial f with respect to y at the point times b. Or this is going to give me what? 6 over root 2. Well, 6 is 3 times 2, so that's 3 times 2 over root 2. Well, that's just 3 root 2. Exactly what we got above. And I think we would agree that this was easier than using the definition even for a simple function, and certainly for a more complicated function. This would definitely be the way to go. So practically speaking, when we compute directional derivatives, we use this approach and certainly not the definition. Okay. So let's work through a couple more example problems just computing directional derivatives. So example 2, compute the directional derivative of f of xy equals x squared sine of 2y at the point 1 comma pi over 2, and in the direction of v equals 3i minus 4j. Now something we want to make sure that we know here, length v is not 1. So when we are looking to compute our directional derivative, we need a direction u that's a unit vector. So typically we kind of reserve the label u in vectors for unit vectors. It's not a guarantee, but it's a notational consideration. So I've called this one v, just noting that we want to go in this direction, but we better construct a unit vector first. So we construct a unit vector by taking the vector in the direction that we want it to point in and dividing by its length. Its length is, of course, 5. 3 squared plus 4 squared is 5 squared. And so u, our unit vector in that same direction as v, is going to be the vector with first component 3/5, second component minus 4/5. I also need the partials of f. Partial f with respect to x is going to be 2x sine of 2y. And the partial with respect to y is going to be, 2x squared cos of 2y. Again, I want to be careful. These are x naught, y naught. And these bits down here are a and b. So I don't want to, accidentally do something like plug 3/5 and minus 4/5 into, the partial derivatives or something like that. I want to make sure I keep straight what's what. So fx at 1 comma pi over 2, well, that's 2 times 1 times sine of 2 times pi over 2 is just sine of pi is 0. And the y partial gives me 2 times 1 squared, or just 2 times cosine of pi, 2 times pi over 2, and that is just minus 2. Cos of pi being minus 1. And again, a and b are 3/5 and minus 4/5 respectively. And I think we have all the pieces we need now to compute our directional derivative. So the directional derivative in the direction u, 3/5 comma minus 4/5, at the point 1 comma pi over 2 is, well, it's going to be 0 times 3/5 plus minus 2 times minus 4/5 is positive 8/5. And that's our answer. Okay, and then example 3, compute the directional derivative at the point 1, 2 for this vector cos of pi over 3 comma sine of pi over 3, which is a unit vector. Again, any vector expressed this way is going to be a unit vector. So again, we'll start by taking our partial derivatives. Partial f with respect to x is going to be negative 2x. And with respect to y is going to be negative 1/2 y. And again, I'll just make a quick note that x naught and y naught are 1 and 2. A and b are these cos and sine numbers over here. In my mind anyway, it's really easy for me to, when I'm looking all over the place and doing a bunch of derivatives, it's easy for me to just grab the wrong x, y, especially because sometimes they even look very similar. Sometimes they're even both written as vectors. It's very easy to grab the wrong one. So taking a couple seconds to just mark out what's what, I think is very helpful in just reducing those types of errors. So fx at 1, 2, when x is 1, this is going to be negative 2. And fy of 1, 2 is going to be negative 1/2 times 2 is negative 1. And I guess we, in theory, could leave this as cos and sine of pi over 3, but let's just figure out what numbers those actually are. I know that pi radians is 180 degrees, pi over 3 radians is 60 degrees. So I'm dealing with a 30, 60, 90 triangle. This is my angle of interest. And I know that this is a 1, 2, square root of 3 type triangle. I know the 1 has to go across from the 30 degrees. That's the smallest number across from the smallest angle. The 2's got to go in the hypotenuse, largest number across from largest angle, and the root 3's got to be over here. And so I see that AB is going to be, well, what? Cos of pi over 3, cosine is the adjacent over hypotenuse, that's 1/2, and the sine opposite of hypotenuse, root 3 over 2. And I think we have everything we need now to compute our directional derivative in this direction, either in the direction pi over 3 or in the direction 1/2 comma root 3 over 2. And that's going to be minus 2 times 1/2 plus negative 1 times root 3 over 2. Well, that's going to give me negative 1 and then minus root 3 over 2. Okay, and then example 4 here. Suppose we have a differentiable function f of xy. Now we know that, again, looking back up above, we know that we picked a direction here. We could, we could describe that direction by theta or by a vector. We picked a specific direction and got a specific directional derivative. If we pick a different direction, we get a different directional derivative. So the directional derivative, the output of that calculation, is a function of the direction I chose. It's essentially a function of this angle theta here. As I vary theta, the output varies as well. And my question here is, in which direction or for which theta do I get the greatest output from the directional derivative? What's the direction of greatest increase? Or if I was thinking of that I was kind of standing on this surface, if I kind of point myself left or right, in what direction should I point myself if I want to go up the steepest direction at this point? So that's what I'm trying to find an example for here. Okay, well, the directional derivative we said was, well, it's fx of x naught y naught times the first component of u. Again, u is a unit vector because it's cos theta sine theta, so we're good there. We do always want to check that, though. We don't want to start plugging in values from a vector that's not a unit vector, but it is here. So times cos of theta plus fy of x naught y naught times sine of theta. And we see that this is, let me clean this up just a tad. We see that this is just some big function of theta. The partials with respect to x and y at the point x naught y naught, at the point under consideration, those are just constants. What's changing here is our direction is changing. We can change theta, and that might increase or decrease the steepness if we start moving in that direction. So how do I maximize f of theta, big F of theta? Well, this is a Calc 1 problem, right? I just have one input. How do I maximize over it? I differentiate, set it equal to 0, and solve. Let me call these, maybe I'll call this, say, alpha, and this, say, beta. So differentiating this with respect to theta gives me negative alpha sine theta plus beta cos theta. And I'll set this equal to 0, look for critical points, and I see I get a critical point when alpha equals cos theta and beta equals sine theta. Or maybe I should say it the other way, when cos theta equals alpha and sine theta equals beta. When I put in alpha here and a beta there, I have minus alpha beta plus alpha beta is equal to 0. That's the critical point I found. What's the second derivative? Well, it's negative alpha cos theta and then minus beta sine theta. And for these choices of cos theta equals alpha and sine theta equals beta, this gives me negative alpha squared minus beta squared, which is less than 0. So we do indeed, we have a critical point and it is a maximum. Now, what's the crux of this problem? I mean, we got an answer, but remember our direction u, we'll call it, say, u max, the direction that maximizes the directional derivative is, well, it's cos theta sine theta. It's actually just alpha comma beta, or it's actually just the first component is the partial of f with respect to x, evaluated x naught y naught, and the second component, the partial of f with respect to y, evaluated at x naught y naught. So the direction that maximizes our directional derivative, that the direction that if we head in that direction will be ascending most steeply, that's the direction that's given by using our partial derivatives for the components of the direction vector. We might also note that the directional derivative in this direction, maybe I'll call this u max, is going to be what? It's going to be fx times cos of theta, but cos of theta, or just the first component of u, is also fx. So we just get fx at x naught y naught squared, and then similarly fy at x naught y naught squared. This is actually just the length of u squared. So pretty interesting. It kind of seems like this maximizer, this direction that maximizes the rate of ascent, is going to be an important idea coming up here, and indeed it is. So we're going to give it a name. We're going to call it the gradient vector. And that's the next little subsection here. So again, recall that we can write the directional derivative as the dot product of a vector where the components are the partials with the vector that's the direction vector. And further, we just showed that this is maximized when we choose the direction vector that is also the vector of the partials. So we define the gradient of f, which is sometimes denoted by this symbol, this kind of upside down triangle f, or just grad f. We define it to be grad f of xy equals, it's the vector where the first component is the partial derivative with respect to the first input in the function, and the second component is the partial derivative with respect to the second input in the function. Okay, so a couple notes for this this idea of a gradient vector. The name of this symbol, this upside down triangle, is called nabla. And the operation that it represents is called del. We're going to be seeing this idea come up quite a bit throughout the rest of the course. So we will want to keep these names in mind. And when I say this here, I'll typically either say grad f, the gradient of f, or del f. So that those are kind of the three primary ways to say it. And then, of course, if you want to say explicitly what your arguments are, you might say something like grad f at xy, or del f at x naught y naught, something like that. Okay, second note, the gradient vector is defined at each point in the 2D domain. So again, assuming our function is differentiable and all of that, keep in mind that in xy, we have a domain for our function f. These are the allowable inputs, right? F is a function of two variables. And at each one of these points, I have a gradient vector. I have a direction of steepest increase on that surface that's above this xy plane. So maybe here it's this way, and maybe here it's that way, and over here it's a different way. At each point, I have a vector in the xy plane. At each point in the xy plane, there's a vector in the xy plane associated with that point. That's the gradient of f at that point. That's going to actually be an important idea. Another way you can think about it is if I have kind of a latitude longitude kind of idea, and I'm walking along kind of a hilly terrain, at each point, latitude and longitude, I have a direction where I would be climbing the hill in the steepest way. So if I am at this point and I'm pointing myself this direction to make the fastest progress, I take a couple of steps forward, I might have to change my direction to a different direction to keep making the fastest progress. And the third note down here, given a level curve, r of t equals x of t, y of t, where f of xy equals k, a real number. So suppose, for instance, that we have some level curves that look like this. Maybe this is like k equals 1. Maybe k equals 2. K equals 3, and so on. So given that we have a particular level curve that we're interested in, where that curve is given by r of t equals x of t, y of t, the claim is that the gradient of f at a given point is perpendicular to the tangent line to the level curve at that same point. So in other words, if I have, say, this point that I'm interested in on the whatever this is, k equals 2 level curve, it has a tangent line at that point, r prime at t naught, where this curve is r of t, r prime at t naught, r of t naught is this point, and then r prime at t naught is what's associated with, it's the direction vector associated with this line here. And the claim is that grad f is perpendicular to that. And again, this is, like I mentioned here, this is a pretty simple derivation. We can just apply the chain rule to f of xy equals k, taking the derivative with respect to t, partial f with respect to x, times dx dt, plus partial f with respect to y, dy dt. And that's got to be equal to 0 because k is constant. So again, as I change t, I'm just going around this level curve, so k stays constant the whole time on that curve. And I note that this left-hand side is just the dot product of the gradient, df dx, df dy, with r prime, with x prime of t, y prime of t. And again, dot product being 0, what does that mean? That means they're perpendicular. Okay, so let's look at example 5 here. So example 5, we have a heat-seeking particle. It's located at the point -2, 3 on the metal plate, whose temperature is given by this temperature function, 20 minus 4x squared minus y squared. So this has the highest temperature at x and y equals 0, 0. As temperature 20 there, and then it kind of, the temperature decreases kind of parabolically as we go away from the origin. And we want to find the path of the particle as it moves in the direction of maximum temperature increase. So our little particle or little bug or whatever it may be is at a point, it kind of searches around itself and says, where's the warmest direction to go in? And it takes a couple steps in that direction, and it turns around again and looks again for the warmest direction, takes a couple of steps in that direction, and that's the path that it's going to follow. So what is its path going to look like? Well, let's let r of t be its path. And it'll be x of t, y of t. We know that the tangent vector at each point in the path is r prime of t which is the x dt and the y dt evaluated at whatever time t. This is the instantaneous direction of travel at time t. So that's the instantaneous direction of travel at time t according to the path r. But what else do we know about the instantaneous direction of travel? Well, we're going to be traveling at a given time t in the direction of maximum temperature increase. but that's in the direction of the gradient. So grad t is, well, it's partial of t with respect to x, negative 8x for the first component, and partial of t with respect to y, negative 2y for the second component. But the tangent vector to the path should be in the same direction as the gradient. These two aren't necessarily equal, but they should be parallel. So we should have the grad t as parallel to r prime. Or in other words, we should have the grad t as, say, kr prime. Well, this gives me two equations. I have negative 8x equals k dx dt, and negative 2y equals k dy dt. Need a little more room here. Note that k is a function of t. So the gradient and the derivative could change magnitude or change relative magnitude as time progresses. I would like to get rid of k. It's not really important for finding the path. If I take the quotient of these two, I get dy dt over dx dt. I would get a k in each of these, but then it divides out. And that gives me negative 2y over negative 8x. But I also note that dy dt over dx dt, well, I can eliminate the parameter there and just get dy by dx equals y over 4x. Okay, little aside on how to solve this differential equation. I think you'll remember this from Calc 2, but just in case you don't, little refresher. So we have 4 over y dy equals 1 over x dx. We can integrate both sides. We're just separating variables here. If you're not familiar with this, you can either review separation of variables, or it's not that big of a deal. It's not all that important for this course. But this gives us 4 log y equals log x plus c. And we get log of y to the fourth equals, well, log x plus c, we could write this as, say, log of some c tilde, some other constant. And then the sum of the logs is the log of the product, so log of c tilde times x. Or I have that y to the fourth, and OneNote just loves correcting my 4s to 9s. Y to the fourth equals, and I'll just get rid of the tilde now, y to the fourth equals cx. We know that we start at the point x equals negative 2, y equals 3, so I have 3 to the fourth equals c times negative 2. And then this gives me c equals negative 81 over 2. So I end up with y to the fourth equals negative 81 over 2 times x. Let's look at a little schematic of what this kind of looks like here. Here's x and y. And my level curves look something like this. These are ellipses that are longer in the y direction than in the x direction. And at the point, what is it? -2, 3. So x equals -2, y equals 3, we're, say, maybe somewhere like here. And then we're following a path that looks like basically x equals -y to the fourth. So it's going to be a parabola opening to the left. We're going to be coming into the origin. Do it the other way. We're going to be coming into the origin along a parabolic curve. And we kind of see, I mean, it's not a perfect picture, but we kind of see that each time we intersect a level curve, it looks like it's at about 90 degrees. And that's what we would expect. We're heading in this direction, going towards the highest temperature. So we're going towards the origin and crossing those level curves at 90-degree angles to follow the gradient. Okay, so that is our, that's kind of a picture of our solution as well as the algebraic solution. All right, so how does all of this apply to functions of 3 variables? Well, we're going to see that this generalizes pretty nicely, especially when we write everything in terms of vectors. So consider we have a function of 3 variables. We want to find the directional derivative in the direction u, which is a vector with 3 components now, ABC, at the point x0, which has 3 components as well. So we define the directional derivative in the direction u of f at point x0, y0, z0, which we'll also define or we'll see is equal to d by dt of f of vector x0 plus t vector u at t equals 0. So this definition just looks exactly the same as the 2-dimensional case. Whether it's 3 dimensions or n dimensions doesn't really matter. But this definition is starting to get a little bit unwieldy. And again, we see that this is going to be the gradient, the equivalent of the gradient, fx, fy, fz, dotted with ABC for exactly the same argument as before, having to do with this d by dt business, just differentiating and then recognizing the result as the dot product of 2 vectors. So analogously to the 2D case, we define grad f for a function of 3 variables to be a vector with 3 components, partial with respect to x, with respect to y, and with respect to z. And note that just as before, the directional derivative of f in the direction u at point x0 is just grad f of x0 dotted with direction u. Okay, a few notes. Again, note that these the vector versions of the definitions extend naturally to functions of 3 or more variables. Keeping things kind of in vector form keeps things tidy, and you don't have to keep track of all of these different components and all of that. So note that here, our gradient and our function have 3 inputs. So here we have a 3-dimensional space. So some, 3-dimensional blob that represents the domain. . Before we had a 2-dimensional domain, And at each point in that two-dimensional domain, we had a gradient vector in that same plane, that same two dimensions, that represented the gradient, the direction of steepest increase. Well, here, at each point in 3 dimensions, we have a vector that represents the gradient, that represents the direction of steepest increase in this 3-dimensional domain. Remember, we're thinking we have 3 inputs that are being mapped over to an output variable. And we're saying that if I'm at this point in 3-dimensional space, moving in this direction in 3-dimensional space, say I'm measuring temperature at a point in a 3-dimensional space, moving in this direction will give me the greatest increase in temperature locally. It'll be where I get the greatest increase in the output over here on the right. It's a completely analogous idea, but it's much harder to draw or to visualize. And again, on that kind of same note, analogous to the 2D case, in functions of 3 variables, instead of having level curves, we have level surfaces. F of x, y, z equals k. That was kind of that picture of the like nested spheres from the book, if you remember that one. We have level surfaces. We have 3 surfaces, 2-dimensional surfaces in 3 dimensions, along which our function is constant. For these surfaces, grad f is orthogonal to the tangent plane to the level surface. In the 2D case, we said grad f was orthogonal to the tangent line to that level curve. Now we have tangent planes to level surfaces, and grad f is orthogonal to that. There's a tangent plane to the level surface, and grad f is normal to it. Okay, so let's look at example 6 here. For a function of n variables, show the directional derivative is maximized in the direction of the gradient vector. This is essentially the same thing that we did in the 2D case, but we're going to do it a little bit differently in the 3D case, just to show 2 different approaches. And then as an exercise, argue that the direction of minimum increase or maximum decrease is in the direction that's opposite the gradient vector. So in other words, if I wanted to, instead of standing on a hill, the kind of hill analogy doesn't work so great here because we're in 3D, but if you just kind of pretend for a second, instead of standing on our hill and trying to find the steepest slope up the hill, where if I walk in that direction, I gain height as quickly as possible, I want to find the direction where I lose height as quickly as possible, the kind of downhill direction, and argue that, as an exercise, argue that that direction, the downhill direction, is the direction opposite the gradient vector. Okay, so the directional derivative in direction u of function f, we said is grad f dot u. My question is, what is the direction u that gives me the the highest directional derivative, the greatest increase? I'm claiming it's the gradient vector. One way to do that was just kind of by brute force. That's basically what I did last time. Here we're going to use a piece of information from chapter 12 where we said, well, the dot product of 2 vectors is the product of the lengths of the vectors. Well, this length is just 1, but times the cosine of the angle in between them. So cos theta, where theta is the angle between grad f and u. For a given point, x naught, y naught, z naught, grad f is constant. Length u is 1, it's constant. So this is just a function of theta, and the only place that theta comes into play is this cosine of theta. Note, of course, that the lengths, both of these lengths are non-negative. So f is going to be maximized when cos of theta is maximized. But cos theta is between -1 and 1. So cos theta is maximized when it's equal to 1. F is maximized when cos theta is equal to 1. And that's whenever theta is 0. But theta 0 says the angle between grad f and u is 0. This says that the direction u is in the direction of grad f, or u equals, say, k squared grad f. So a positive constant times the gradient. U is in the same direction as the gradient in order to maximize our increase. So this is another way to show, maybe a little more subtle, maybe a little more elegant way to show that the gradient vector is the direction of maximal increase. Okay, and then example 7, a pretty straightforward example to end on. Find the direction of maximum increase of the function f of x, y, z equals x squared plus y squared minus 4z at the point 2 minus 1, 1. And so what do we need to do? We need to find grad f at 2 minus 1, 1. Grad f, first component is df dx, just 2x. Second component, partial f with respect to y, just 2y. And third component, partial with respect to z, just -4. And grad f of 2 minus 1, 1 is 4 comma -2 comma 4. So we want to head in this direction in three-dimensional space to achieve the maximum increase of my function when I'm at this point. Okay, so that's the supplement on directional derivatives and gradients. Certainly important topics. I think, for the most part, fairly straightforward, especially relative to the chain rule. I think the chain rule is a bit more complicated. There's a couple different chain rules in the bookkeeping and so on. So I think this is a nice little break from that. And then in tomorrow's class, we'll start talking about maxes and mins. And again, the last supplement for the week will be on Lagrange multiplier method.